Welcome back to Math Kernel. Once a space has a scalar product, it has geometry, length, angle, perpendicularity. This set drills all of it, computing angles the way the exam actually asks, using Cauchy-Schwarz and its equality case, the bilinear identities, the parallelogram test for whether a norm even comes from a scalar product, orthogonality and Pythagoras, and the two proofs your professor expects cold. 12 problems. Pause whenever you want to try one first. Problem 1. The most basic geometry question. Find the angle between two vectors. Pause and try. The angle always comes from the same formula. The cosine of phi is the scalar product over the product of the two lengths. That formula is well defined precisely because Cauchy-Schwarz guarantees the fraction stays between -1 and 1. So compute the pieces. The scalar product, 2 times 1 plus 0 times 1, 2. The lengths x has length 2, and y is the root of 1 plus 1, root 2. Assemble 2 over 2 root 2, which simplifies to 1 over root 2. And 1 over root 2 is the cosine of 45 degrees. The angle is 45 degrees, exactly what the picture shows. Problem 2. This is how angles really show up in the exam, as the rotation angle of an isometry. After projecting off the axis, you're left with two in-plane vectors, and the rotation angle is just the angle between them. Pause and try. The key realization: the rotation angle is nothing new. It's the ordinary angle between the two in-plane vectors from the very same formula. Compute the scalar product of u1 and u2, 1 times 1 plus 0 plus 0, 1. Each in-plane vector has length root 2. So the cosine is 1 over root 2 times root 2, which is 1/2. Cosine 1/2 is 60 degrees. That's the rotation angle. Recognize this pattern. Nearly every angle the exam asks for is really this computation wearing an isometry costume. Problem 3. Verify Cauchy-Schwarz on concrete vectors, that the size of the scalar product never exceeds the product of the lengths. Pause and try. Cauchy-Schwarz says the absolute value of the scalar product is at most the product of the lengths. Just compute both sides and compare. Left side, the scalar product, 2 times 0 plus 2 times 3 plus 1 times 4, 10. Right side, the two lengths. X is the root of 4 plus 4 plus 1, 3. Y is the root of 9 plus 16, 5. Compare. 10 is less than or equal to 3 times 5, 15. The inequality holds. And it's strict. 10 is strictly below 15 because the two vectors aren't parallel. Equality would require one to be a multiple of the other, which brings us to the next problem. Problem 4. Cauchy-Schwarz becomes an equality in exactly one situation. Test these two vectors and explain what you see. Pause and try. First, look before you compute. Y is -2 times x. The second vector is just the first, scaled. They're linearly dependent. Left side. The scalar product is -2, -8, -2, so -12. Its absolute value is 12. Right side x has length root 6, and y, being twice as long, has length root 24, which is 2 root 6. Their product is 2 times 6, 12. 12 equals 12, equality. And that's the whole content of the equality case. Cauchy-Schwarz is an equality exactly when the two vectors are linearly dependent, lying on a single line. Not parallel, and it's strict, parallel, and it's exact. Problem 5. No coordinates this time, just 3 numbers. Expand the squared norms using bilinearity. Pause and try. Bilinearity gives the same binomial pattern you know from numbers. The squared norm of x plus y is the norm of x squared, plus twice the scalar product, plus the norm of y squared. It's exactly a plus b squared, but the middle term is a scalar product. For the plus, 9 plus twice minus 4 plus 25. That's 9 minus 8 plus 25, 26. For the minus, watch the sign carefully. Minus times a negative scalar product becomes plus 8. 9 plus 8 plus 25, 42. 26 and 42. The whole trick is that the cross term carries the sign of the scalar product, and here that product is negative, so subtracting the vectors makes them longer apart, not shorter. Problem 6. The reverse direction. You're given 2 lengths and must extract the scalar product hiding between them. This is the polarization identity. Pause and try. Take the 2 expansions from the last problem and subtract them. The norm squared terms cancel, and the 2 cross terms add up. What's left is 4 times the scalar product. Rearrange, and you get the polarization identity. The scalar product is 1/4 of the norm of x plus y squared minus the norm of x minus y squared. It literally reconstructs the product from lengths alone. Plug in the 2 given numbers. 1/4 of 20 minus 8. 1/4 of 12, 3. The scalar product is 3, pulled out of pure length information. This is why a norm secretly remembers all the angles. They're encoded in the lengths of sums and differences. Problem 7, a subtle one. Not every norm comes from a scalar product. The test is the parallelogram law. If it fails, no scalar product can exist that induces the norm. Check the maximum norm. Pause and try. Here's the litmus test. Every norm that comes from a scalar product must satisfy the parallelogram law. The sum of the squared diagonals of a parallelogram equals twice the sum of the squared sides. If a norm breaks this even once, no scalar product can induce it. Use the maximum norm, the largest absolute component. For x plus y, that's 1, 1, whose maximum is 1. For x minus y, 1, minus 1, again maximum 1. Left side of the law, 1 squared plus 1 squared, 2. Right side, twice 1 plus twice 1, 4. 2 is not 4. The law fails, so the maximum norm is not induced by any scalar product. Geometrically, its unit ball is a square, not a round circle, and only round unit balls come from scalar products. The Euclidean norm, whose ball is the circle, passes the very same test. Problem 8. The triangle inequality and its lesser-known reverse on concrete vectors. Pause and try. Compute the 3 lengths first. X is 3, y is 4, and their sum, 3, 4 has length 5. Triangle inequality. The length of the sum, 5, is at most the sum of the lengths, 7. It holds, with room to spare, because the 2 vectors point in different directions. The reverse triangle inequality bounds from below. The size of the difference of the lengths, that's 1, is at most the length of the difference, 5. Also true. When would the triangle inequality be an equality? 5 equals 7. Only if the vectors point the exact same way, y a non-negative multiple of x. A straight detour is no shorter than the direct path, and only a genuinely straight one ties. Problem 9. The cheapest recurring points on the exam. Checking that 2 vectors are perpendicular and confirming Pythagoras follows. Pause and try. Perpendicularity is one scalar product away. Compute V with W. 1 minus 1 plus 1 minus 1, 0. A zero scalar product means the vectors are orthogonal, even in 4 dimensions where you can't picture it. Now the length squared. V with itself is 4, W with itself is 4. Add the vectors 2, 0, 2, 0, whose length squared is 4 plus 4, 8. And 8 equals 4 plus 4. The squared length of the sum equals the sum of the squared lengths, Pythagoras. It holds precisely because the cross term, twice the scalar product, vanished when the vectors were perpendicular. Orthogonality and Pythagoras are the same fact. Problem 10. 2 classical results. First, confirm the cosine rule on real vectors. Then prove Thales that any triangle inscribed in a semicircle has a right angle. Pause and try. Part A. The cosine rule, the scalar product version of the law you know from trigonometry. The squared length of the difference is the sum of the squared lengths, minus twice their product times the cosine. Here both vectors have length 2, and their scalar product is 2, so the cosine is 1/2, a 60-degree angle. Check both sides. The difference x minus y is 1 minus root 3 with squared length 4. And the formula gives 4 plus 4 minus 2 times 2 times 2 times 1/2. That's 8 minus 4, 4. They agree. Part B. Thales. Put the circle's center at the origin, so the diameter endpoints satisfy b equals minus a. Then c minus b is c plus a, and the scalar product of c minus a with c plus a is a difference of squares, the norm of c squared minus the norm of a squared. But c and a both sit on the circle of radius 2, so both norms are 2. The difference is 0. A zero scalar product means the two sides from C are perpendicular. The angle in the semicircle is a right angle. That's Thales in 3 lines of algebra. Problem 11. The flagship proof, the one your professor expects cold. Prove Cauchy-Schwarz from the axioms, using the trick of a well-chosen non-negative quantity. Pause and try to reconstruct it. Start by clearing the trivial case. If y is the zero vector, both sides are 0 and the inequality holds. So assume y is non-zero. Now the idea the whole proof hinges on. Build a quantity that is obviously non-negative. Take g of t, the squared norm of x minus ty. A squared norm is never negative for any real t. Expand it with the binomial identity. You get a parabola in t, the norm of x squared, minus 2t times the scalar product, plus t squared times the norm of y squared. It opens upward, and it never dips below 0. An upward parabola that stays non-negative is smallest at its vertex, and even there it's at least 0. Plug in the minimizing t star, the scalar product over the norm of y squared, and the minimum value is the norm of x squared minus the scalar product squared over the norm of y squared, and that must be at least 0. Clear the denominator. The scalar product squared is at most the norm of x squared times the norm of y squared. Take square roots, and there it is. The absolute value of the scalar product is at most the product of the lengths. Cauchy-Schwarz. And notice the equality case falls out for free. Equality means the minimum of g is exactly 0, which means x minus t star y is the zero vector. The vectors are dependent. Problem 12, the last one, and it's a 2-line payoff once you have Cauchy-Schwarz. Prove the triangle inequality. Pause and try. Start from what you want to bound, the squared norm of x plus y, and expand it with the binomial identity, norm of x squared, plus twice the scalar product, plus norm of y squared. The only troublesome term is the middle one. Cross two bridges. The scalar product is at most its own absolute value, and by Cauchy-Schwarz that absolute value is at most the product of the lengths. Replace the middle term by that upper bound, and the right-hand side becomes a perfect square. Norm of x squared plus twice norm x norm y plus norm of y squared, exactly the norm of x plus the norm of y, all squared. Take square roots of both sides, and the triangle inequality drops out. The length of the sum is at most the sum of the lengths. Notice the engine of the whole argument was Cauchy-Schwarz, bound the one cross term, and geometry does the rest. That's why those two proofs travel together. That's the geometry of the scalar product, end to end. The habits to carry, the angle formula, and that it's really the rotation angle computation in disguise. Cauchy-Schwarz with its equality case being linear dependence, the binomial identities, and the polarization trick. The parallelogram law as the test for whether a norm even comes from a scalar product. Orthogonality as a single zero, with Pythagoras riding along, and the two proofs. Cauchy-Schwarz from the non-negative parabola, and the triangle inequality riding on its back. See you in the next one.